All right, so now we're going to add the complication of friction. And this, we're not really going to change the way we work the problems, but now we'll have a separate force that to include to make things a little more, I don't know, interesting or realistic. First of all, we have two types of friction, just sort of two broad categories of friction. And this is just sort of, I think it's kind of interesting. You have macroscopic friction, and you have microscopic friction. Now, macroscopic, of course, means big, and microscopic means small. So you can think about the difference in these. Now, first imagine that we have two surfaces. They're jagged surfaces. They come together, and these teeth sort of catch on one another as they're trying to move in their opposing directions. They both feel a force that's opposing their motion. All right, and that's that frictional force, and it's due to the macroscopic causes, these just sort of jagged edges catching on one another. Now, as you might expect, if you were to plot the frictional force, which, by the way, we usually label with a lowercase script f, versus the smoothness, that is, if I were to have these surfaces smoothed like this, then as I move them with respect to one another, then they're going to experience less friction. So if I plot the frictional force versus the smoothness, it'll look something like that. I'm not sure what the function is exactly, but as you increase the smoothness, the amount of friction decreases. Now, an interesting thing happens, that as you make it more and more smooth, then you begin to get a little increase here. Oh, not like that. You get a little increase where the frictional forces at some point will begin to increase. Now, this is due to two causes. Now, first of all, you have a greater contact area. As you smooth them, more of the surfaces come into contact with one another, and that causes more surfaces to actually interact with one another. And closely related to that is that as you get that greater contact area, and as the surfaces get closer and closer and closer to one another, you actually get electric forces become involved more prominently. And so, for example, if you have a positive charge over here and a negative charge over here, those two charges are going to tend to be attracted to one another, and you'll cause an increase in your frictional force as those intermolecular forces begin to begin to be more prominent. All right, a couple of things about friction. It's always opposite the direction of motion. So if I have an object that's sitting here and I'm moving it this direction with a certain force, and if there's a frictional force, the frictional force will be the opposite direction. Now, that's true if it's moving in that direction, or if v equals 0. Now, if v equals 0, the force is there, it's just not an unbalanced force. The frictional force is there, it's just it completely balances with the force that you're pushing on the object with. More about that in just a moment. All right, so we'll come back to that. But just remember, friction is always opposite the direction of motion. Now, there are two types of friction. First of all, static friction. We call this Fs. And static friction acts on objects that, of course, are stationary. All right, static friction acts on objects that are stationary. We can calculate our static friction in this way. Fs, so I'm going to write it in two different ways. I'll write it as Fs max equals mu s times my normal force. All right, so mu s is called the coefficient of static friction. Coefficient of static friction. And of course, the normal force is, well, the force that's being pushed up by the surface, which we've already talked about. Now, this coefficient of static friction is experimental. The way they do this, and we'll do this in lab, is you measure the static frictional force, you measure the normal force, and you plot this. You have some data points. You plot it. You find the slope, and the slope is equal to mu. And that's done experimentally. There are no units for mu. Notice that I have newtons on the left and newtons on the right. So there are no units. It's merely a ratio of the static frictional force to the normal force. Now, let's return to this because I wasn't entirely clear with you. This is my maximum static frictional force. Imagine that I have an object and I'm trying to push it across a surface. I apply a certain force to that object. All right, but let's say that force isn't big enough to cause it to move. That means that I have a static frictional force that's opposing it, all right? Because otherwise, if I didn't have an opposite force, then it would move. But this is a stationary object. It has a velocity equal to 0. If it's not moving, I know that static friction is relevant. Now, this force, let's say that it's equal to 2 newtons. Then I know that my static frictional force is, well, it's 2 newtons. But then let's say I push with a bigger force. Say I push with 3 newtons, and it still doesn't move. That means my static frictional force is 3 newtons. Or I push with 5 newtons, and it still doesn't move. That means that my static frictional force is 5 newtons. Okay, so there is a whole range of static frictional forces that go up to some maximum value. And this is how you determine that maximum value. A more general way to write the static frictional force would be to say this, that Fs is less than or equal to mu s times the normal force. And then when you reach that maximum static frictional force, that's a product of the coefficient and the normal force, any force over that maximum will cause the object to move. All right, you experience this, right? Like when you push an object across the floor, all right? You're back here, you're pushing. You're trying to push this big old object. You're not very happy about it because it's too big. And you push and push and push until you overcome the static frictional force, and then the object begins to move. We'll come back to that. All right, so you have to overcome the static frictional force to move an object. All right, now, kinetic friction. Kinetic friction, we use that lowercase script f. We put a k on it. It's on objects that are moving. All right. Let's return back to this guy pushing a box. Now he's happy because he gets it to move. All right, after he begins to get it moving, we'll say it has some velocity in that direction, then our kinetic frictional force will be acting in this direction. So the guy is pushing on a force in this direction, and you have a kinetic frictional force that's the opposite direction. It can be that F is equal to Fk, right? That means it can be that the acceleration is 0, so A can be 0. But the velocity has to be greater than 0 for kinetic friction to apply. We can calculate our kinetic friction. You probably figured this already, but it's equal to mu k times the normal force. So now instead of mu s, like we had before, we have mu k. And this, of course, is the coefficient of kinetic friction. All right, it's determined experimentally. You'll do that in lab. So I'm not sure if in lab you determine the static or kinetic, I forget, but you determine one of those. And it's done in the same way. All right, now for almost all materials, mu s is greater than mu k. For almost all materials, mu s is greater than mu k. This becomes really apparent when you apply the brakes in your car. So imagine that you're driving. I know that most of you don't really stop at stop signs, but if you did, and maybe you'll do this after this class, you would see that this happens. All right, here's your stop sign. Stop. All right, you come to a stop. You're coming, and you slowly come to a stop. And at that point, just before you come to a stop, your car is going, and then it jerks forward a little bit, and it comes back. That's this transition that you're making from kinetic friction you're going from mu k, or Fk, to static friction. Because your car, your brake system has these metal rotors, and there are these brake pads that clamp down onto those rotors. As long as your car is moving, then the friction that is relevant is the kinetic friction. But when it comes to a complete rest, static friction comes into play. Okay? And because they're different, static and kinetic friction, there's this discontinuity between the two. And that's what you experience when you sort of jerk forward just a little bit as you come to a stop. So try it today when you go out. Just come slowly to a stop at a stop sign or red light, and notice that you sort of jerk just a little bit. This is relevant in cars for another reason too. When you're braking, now imagine that you have your tire here of your car, and it's moving in this direction. It's rotating around in that direction. The surface of the road and the tire are stationary with respect to one another. So these two surfaces are stationary. And it's a good thing because the relevant forces here that propel you forward, let's see if I can get this right, the static frictional force, that's right, is in that direction. That's what causes you to propel you forward. And because that static frictional force is larger than the kinetic frictional force, you get a better grip on the road. All right. This, of course, is the reasoning behind anti-lock brake systems, ABS, anti-lock brake systems. Now, in old cars that didn't have anti-lock brake systems, if you wanted to come to a very quick stop, you had to pump the brakes. You had to pump the brakes off and on, off and on, off and on, as you know, at a fairly fast pace. And that would cause the wheels to not lock up. Because if the wheels lock up, that causes you to skid. And of course, then if they're skidding, if your tires aren't rolling, but they're skidding, sliding across the pavement, that's kinetic friction. And kinetic friction isn't as powerful, isn't as strong as static friction. So you can't grip the road as easily. So these ABS brakes actually have little actuators in the brake pads that when you slam on the brake pedal, they go off, on, off, on, off, on, off, on, off, on, and make the effect of pumping the brakes. But it does it for you in a much more efficient way. So those are ABS brakes. You can watch a clip from the women's triathlon from the Olympics last year where the women were crashing. And if you'll notice that when you crash on a bicycle, at least in these cases, that it's not that you're skidding forward, but that you're skidding sideways. And so when you skid sideways on a bicycle or on a car for that matter, that occurs when the kinetic friction comes into play, that you start to skid, which of course is that kinetic friction. Well, just watch this short clip. Here you go. I'll start at the appropriate time. All right, well, let's look at this example. This is a quick example, but I have this block on a table, and a force is pulling on the block, but the block is not moving. I want to know what is the maximum force F so that the block will stay stationary. So I've already drawn all the forces. I'm just going to redraw them on a coordinate grid. So I have my normal force here, I have my force here, my static frictional force, and my weight. Then I can apply Newton's second law. So this, by the way, would be step number 2. This is step number 1. We're just labeling all the forces. There is no step number 3 because they're all on axis, so I don't need to resolve any vectors. So I'm going to skip straight to step 4. The sum of the forces in the x direction equals max. Now ax is equal to 0, so this will just be equal to 0. And that's going to be F minus Fs equals 0. In a similar way, I can write the sum of the forces in the y direction equals may, and that's equal to 0. And the sum of the forces in y are going to be the normal force minus the weight equals 0. All right, I want to know what is the coefficient of static friction. Let's see, the force I think is given. I want to know what is the maximum force. So I want to find F. Now the maximum force without moving it is a force that's equal to the static frictional force. And I know that that static frictional force is equal to mu s times my normal force. Of course, I don't know my normal force, so I'll go over here, and I can find that the normal force is equal to the weight, which is equal to the mass times gravity. My mass was 1 kilogram, so I'll call this 1 times 9.8 meters per second squared, or I'll just call it 10 newtons. So that's my normal force, and now I can find my force over here. I have a coefficient of 0.1 times my normal force of 10 newtons, so it's going to be just 1 newton. So the force required to move that block from the table is just 1 newton.